Finally, we got through all weeks. Well, we have one more to go, which is today. So this is the 10th week of the 10-week challenge. But either way, congrats on hanging tight, staying here all this time. I wish you well in your IB math exams. We're gonna go through these 5 questions today, the last 5 questions today. But let me just take this time to wish you best of luck in your IB math exam. If you stayed up to here, that means that you've practiced a lot. And if you've practiced a lot, trust me, you're in a very good position. There's no need to be anxious. There's no need to be nervous. Just perform at your best. So again, we still have this week to cover 5 different questions from 5 different IB math topics. We're gonna go through them right now. If you've missed any, you can check the links in the description of this video. So let's get to it. Let's get through the last week of the ACE or IB math exams in 10 weeks. All right, so let's start with exercise number 1, which involves complex numbers. Consider the complex number z equals cosine of theta plus I sine of theta. Now we know, and we can always evaluate that to make sure, but well, not to make sure, but to actually verify that the modulus of this complex number is equal to 1. How do we find the modulus? If you take a complex number a plus bi, its modulus is given by the real part squared plus the imaginary part squared, all that inside a square root. In this case, the real part is cosine of theta, the imaginary part is sine of theta. Therefore, its modulus is the square root of cosine squared plus sine squared. We know that sine squared plus cosine squared is equal to 1. Therefore, it is the root of 1, which is, of course, equal to 1. Now, the argument is the angle, which is theta. Now, what we need to do in this exercise, or at least in question A, is by using the Moivre's theorem and the binomial theorem, show that cosine of 3 theta is equal to 4 cos cubed of theta minus 3 cosine of theta. This is a classic exercise, one that involves complex numbers, more specifically the Moivre's theorem and binomial expansions. We're going to do both things side by side and do the equivalency of the real part with the real part and the imaginary part with the imaginary part, which is going to become more clear as we go. Now, know that you can also write cosine of theta plus I sine of theta as cis theta, which means cosine imaginary sine. This is another notation that we can use. Now, if we cube this complex number here, z, that is equivalent to cubing this or cubing this, given that this and this, well, they're the same. So let's start with that. Z cubed is equal to cis of theta cubed, which is also equal to cosine theta plus I sine of theta cubed. And by using the Moivre's theorem, which is also in your formula booklet, we can say that cis theta cubed is the same thing as cis of 3 theta. Know that when you're applying this formula, the modulus, which is expressed by r in this formula here, is equal to 1, which is the modulus that we found before. So what happened here was, given that z is equal to 1 cis of theta, when we cube it, we get 1 cubed times cis of 3 times theta, which is exactly what we have right here. Now, on the right side, or the right-hand side, we have a binomial expansion. And to do that, it is convenient that you remember Pascal's triangle up to the 3rd row, which is this right here, 1, 3, 3, 1. When you're expanding a plus b cubed, a and b, just as placeholders for this expansion, we have 1a cubed plus 3a squared b plus 3ab squared plus b cubed. Therefore, on the right-hand side, we have cos cubed of theta plus 3 cosine squared of theta times I sine theta plus 3 cosine of theta, I sine of theta squared plus 1 sine cubed of theta times I cubed, or I sine theta cubed, which is the same thing. We can simplify a few things here. We can rewrite this as I squared sine squared, which is the same as negative sine squared of theta, given that I squared is equal to negative 1. We can rewrite this as I cubed sine cubed of theta, which is the same as I squared times I times sine cubed of theta. Given that I squared is equal to negative 1, we can finally rewrite all of this as negative I sine cubed of theta. Therefore, we have cis of 3 theta as cos cubed of theta plus 3i cos squared sine theta minus 3 cos theta sine squared of theta minus I sine cubed of theta. Now this is right here on the left hand side can be rewritten as cosine of 3 theta, given that it's new argument, plus I sine of 3 theta. Therefore, cos of 3 theta plus I sine of 3 theta is equal to what we got from before, cos cubed plus 3I cos squared sine minus 3, and so on and so forth. Knowing that for this equation to be true, the real part of the left-hand side has to be equal to the real part of the right-hand side, and the same thing needs to happen with the imaginary one. Therefore, cos of 3 theta has to be equal to cos cubed minus 3 cos theta sine squared, which are the real parts of the right-hand side. Now, if we take the imaginary parts of the left-hand side, well, it needs to be equal to the imaginary part of the right-hand side. Therefore, cos of 3 theta is cos cubed minus 3 cos theta sine squared. And sine of 3 theta is equal to 3 cos squared sine theta minus sine cubed of theta. And this is close to what we need to prove, but not quite that. There's still one adjustment to make, which is, notice that in the description of the exercise, cos of 3 theta is written in terms of cos only. Therefore, we're going to switch, or we're going to change or substitute this sine squared of theta by 1 minus cos squared of theta, which is the Pythagorean identity. Now, as you distribute the 3 cosine of theta, you get 4 cos cubed minus 3 cos theta. And that's it. This is question A. Now, on question B, we got to show that cos of 6 theta is 32 cos to the 6th minus 48 cos to the 4th plus 18 cos squared minus 1, which is not a friendly expression. To do that, we're going to start with the double angle identity. We know that cosine of 2 times an angle, let me call this alpha for now, is equal to 2 cos squared of alpha minus 1, which means that if we replace this alpha by 3 theta, we get cos of 2 times 3 theta, which is 6 theta, equals 2 cos squared of 3 theta minus 1, which is 2 times whatever we got from before, which is 4 cosine cubed of theta minus 3 cosine of theta squared minus 1. Now the rest is just algebra. 16 cos to the 6th, 24 cos to the 4th, 9 cos squared. And then by multiplying this by 2 and subtracting 1, we finally get the result, which is 32 cos to the 6th minus 48 cos to the 4th plus 18 cos squared minus 1. And that's it. Now, moving on to question C. Consider the solutions of the equation cos of 6 theta equals 0 in the first and second quadrants. Now, we need to find the solutions of cos of 6 theta equals 0 in these two quadrants. One thing to be careful here is whenever you change the arc from x to 2x or from theta to 6 theta, for example, the search radius, let's say, of the solution is not going to be from 0 to pi anymore. You got to multiply this whole interval by 6 in this case, because in the end you're going to divide by 6. So in the end it's going to be contained in between 0 and pi. What do I mean by that? You're trying to solve cosine of 6 theta equals 0 in this interval right here from 0 to pi. Given that we have a 6 theta here, we're going to multiply this interval, both of these numbers, 0 and pi, by 6. So this one by 6, this one by 6, and this one by 6 because it got multiplied by 6. The argument or the arc is now 6 theta. When we're trying to find the solutions for this equation, we're going to go from 0 to 6 pi to find those solutions. In the end, we're going to divide everything by 6. Now, where's cosine equal to 0? If we draw or sketch a unit circle, and starting from 0, let me use a different color here, which is this angle right here, the cosine is equal to 1 when theta is 0. Now when theta is equal to pi over 2, that's when cosine is equal to 0. Then pi doesn't work. 3 pi over 2, yes, cosine is 0. And then 2 pi, it's equal to 1 again. We cannot stop here. We have to go all the way not to 2 pi, but to 6 pi. We're going to circle this twice more. Now, we have 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2 as solutions as well, wherever we hit these 2 points. So 6 theta is pi over 2, 3 pi over 2, 5 and 7, pi over 2, 9 pi over 2, and 11 pi over 2. Therefore, theta is all of these arcs, all of these angles divided by 6. So we have pi over 12, all of these guys over 12. Now, do you know that 3 pi over 12, well, this guy can be rewritten as pi over 4, and 9 pi over 12, this is 3 pi over 4. Now notice that all of these arcs, all of these angles, they are in between 0 and pi, which is the original interval. Now, moving to the last question, which is question D. Find the exact value of cosine of pi over 12 times cosine of 5 pi over 12 times cosine of 7 pi over 12 times cosine of 11 pi over 12. It is no coincidence that the angles, the arcs that show up here, are the same ones that showed up in the previous answer. The solutions for cosine of 6 theta equals 0 are these arcs with the addition of these other two, 3 pi over 12 and 9 pi over 12, which by the way are pi over 4 and 3 pi over 4. In addition to that, notice as well that you already proved that cosine of 6 theta equals 32 cosine to the 6th, and so on and so forth. Therefore, solving this equals 0 is the same thing as solving this equals 0. Therefore, and starting with that, the solutions of cosine of 6 theta equals 0, they are also solutions or roots of this equal to 0 as well. Now, the fastest way to solve this problem is to use sum and product, and in this case, using the product of roots. Let's remember that for a polynomial of the nth degree, the product of the roots is equal to -1 to the power of 6. In this case, this is the order of the polynomial times the constant term, which is a to the 0, which is -1 in this case, over the leading coefficient, which is 32. There's just one adaptation that we're going to make, which is to substitute cosine of theta by x. If that is the case, the solutions are not pi over 12, 3 pi over 12, and so on anymore. They're actually, for this equation right here, the cosine of all of these angles. So these are all solutions to this equation right here. All right, so what is the product of these roots? The product, which is the product of all of these roots, is equal to -1 to the 6th times -1, which is the constant of the polynomial, over the leading coefficient, which is 32. There are two more things that we need to substitute, two more values. Cosine of 3 pi over 12 is cosine of pi over 4. It's the same thing, which is root of 2 over 2. Also, cosine of 9 pi over 12 is cosine of 3 pi over 4, which is negative root 2 over 2. Therefore, this product right here is equal, and by the way, this times this is -½ and this is -1 over 32. Therefore, these cosines times -½ they're equal to -1 over 32. Therefore, and finally, the product of the cosines mentioned in the exercise, it is equal to 1 over 16. And that is it for this long exercise number 1. All right, so let's move to exercise 2, one that involves complex numbers. We have to express in question A 3 minus I root 3 in the form r e to the I theta. Now, this is Euler form, so Euler form where the modulus is greater than 0, of course, and the argument is in between -pi and pi, including pi. Now, the way to express this is to find the modulus and the argument of this complex number. To do so, for the modulus, we square root the real part squared plus the imaginary part of this number squared as well. So we have the root of 9 plus 3, which is root of 12, which can also be expressed as 2 root 3. And then we have the argument. One suggestion that I always make is whenever you're calculating the argument, do a rough sketch of where this complex number is. It is a complex number which has a real part which is positive, so positive 3, and an imaginary part which is negative root of 3. So this angle right here will be negative whatever this angle is. And what is this angle? It is the arc tan of imaginary part over real part. Do notice that I never included the negative in the root of 3 inside this arc tan because we already took into account the sign when we created this diagram. So negative arc tan of root 3 over 3 is pi over 6, so negative pi over 6. Therefore, we can express z as 2 root of 3 times e to the I negative pi over 6. All right, so let's move to question B now. Given that 3 minus I root of 3 is a zero of this function right here, this polynomial right here, find the other three zeros. Now, we know, or we should know, that if we have a complex root as a root of a, well, not a root, but a zero of a polynomial, then its complex conjugate will also be a zero. Therefore, two of the zeros are 3 minus I root of 3 and 3 plus I root of 3. We have a polynomial of the fourth degree. Therefore, according to the fundamental theorem of algebra, we have 4 roots. And as mentioned before, these are 2 of them. So these make up for a quadratic term. We have a quadratic term times something. It could be another quadratic term if the other 2 roots are complex roots, or a quadratic term times a linear times another linear if the other 2 roots are real. Now, let me illustrate this as f of x being equal to a quadratic term times something. And as I mentioned before, this something could be another quadratic or 2 others. I just wrote this so I could illustrate the calculation of this quadratic term. This quadratic term will have these 2 roots as mentioned before, or these 2 zeros as mentioned before, and we're going to use sum and product to come up with this quadratic. Now, the sum of these 2 roots is 3 minus I root of 3 plus 3 plus I root of 3, which is equal to 6. The imaginary parts will cancel out, whereas the product of these terms, or of these roots or zeros, it is 9 plus 3I root of 3 minus 3I root of 3, which will cancel out, minus I squared times root of 3 times root of 3, which is equal to 3. I squared is equal to negative 1. Therefore, we have 12 as the product of these 2 roots. Therefore, this quadratic term is x squared minus the sum times x plus the product. Why is that the case? If you have a quadratic in the form x squared plus bx plus c, the sum of the roots is negative b over a, which in this case is equal to 1, and the product is c over a. That's why we can write this negative 6 as b, given that b is negative sum, and the product as c, given that c is equal to the product. Notice that a is equal to 1 in this case, and it should be, because we are considering that this 2 will be produced by this other quadratic or these other linear terms. We can do that, that's fine. Now, given that this quadratic is part of the quartic of the 4th degree polynomial, we're going to carry out a polynomial division to find this other guy over here. How do we do that? Long division. So dividing f of x by x squared minus 6x plus 12. And this division, by the way, has to produce a remainder of 0, given that x squared minus 6x plus 12 is a factor of this quartic f of x right here. We're going to have 2x squared, which is what we need to multiply this to get this. So our 2x to the 4th. By the way, if you're not familiar with long division, you should be. This is a very important skill to have in this curriculum. And we continue the multiplications by negative 6x and positive 12. So negative 12x cubed plus 24x squared. By subtracting, we get rid of this, and we're left with 5x cubed minus 33x squared plus 78x minus 36. Now, in order to get this 5x cubed, we're going to add a 5x over here, because the product by x squared will create a 5x cubed. So we get 5x cubed, which is the product right here, minus 30x squared plus 60x. So we have negative 3x squared plus 18x minus 36. And lastly, we should multiply x squared by negative 3. So we get negative 3x squared plus 18x minus 36, and the subtraction will produce a 0, which is expected. The remainder should be 0, as mentioned before. Therefore, our f of x can be written as x squared minus 6x plus 12, which is the quadratic factor that we knew from before, times 2x squared plus 5x minus 3. We could factor this into x plus 3 times 2x minus 1, which would make it easier to find the roots as well. Or we could just solve this quadratic because the exercise is asking for the other zeros, the other roots. Now, either way, it's fine. The zeros are negative 3 and 1 over 2, and that's all there is to it. All right, so let's get to exercise number 3, a demanding vectors exercise. So this one involves vectors and lines, and a third line which is perpendicular to the first two. So let's get to it. Consider the two lines L1 and L2, which are illustrated, by the way, in the diagram. The parametric equations of these lines, they are given right here and right here. Find the value of alpha for which the lines L1 and L2 intersect, and find the coordinates of their point of intersection P. Now, if they intersect, they occupy the same place, the same position in space, which means that they're going to share the same x, y, and z coordinates at the same time. Therefore, whenever they intersect, or wherever they intersect, 7 plus 2 lambda will be equal to negative 1 plus 3 mu, and also 2 plus lambda will be equal to 2 plus mu, and also alpha plus lambda will be equal to negative 1 plus 2 mu. Now, the easiest way to solve this system is to start with this equation number 2. We can cancel out the 2's over here, and we know that lambda will be equal to mu where these lines intersect. Now, plugging this into the first equation, we get 7 plus 2 lambda equals negative 1 plus 3 times mu, but mu is equal to lambda, so 3 times lambda. We have lambda equal to 8. And by the way, remember that lambda and mu, they're the same. Now, substituting these two values into equation number 3, we get alpha plus lambda equals negative 1 plus 2 times mu, so 2 times 8. Therefore, alpha will be equal to 7. Now, to find the point P, which is the point of intersection, we can plug in lambda and alpha over here, or we can just plug in mu over here, meaning that the x-coordinate will be negative 1 plus 3 times lambda, which is 23, 2 plus mu, which is equal to 10, and negative 1 plus 2 times mu, which is 15. So that is it. Exercise A was answered. Now let's move to question B, or exercise B. For the remainder of the question, we're going to consider alpha to be equal to 2, which is exactly what's stated over here. So let me go back to the equation L1 and substitute this by 2. Let A be a point in L1 and B be a point in L2. Show that BA, the vector BA, can be written in terms of lambda and mu as such. Now, where did he take this from? Any point that belongs to line L1 will have the following recipe. This is the general form of the point. It's going to be 7 plus 2 lambda. And by the way, this is point A, which is the point that the line L1 crosses. The y-coordinate is 2 plus lambda, and the z-coordinate will be 2 plus lambda as well. Now for L2, which gives us the general point of any point that the general point for L2, any point that belongs to line 2, will have also the following recipe: negative 1 plus 3 mu, comma 2 plus mu, comma negative 1 plus 2 mu. Now, if we build a vector which connects these 2 points, or a vector which is formed by these 2 points, in this case vector BA, we just need to subtract from the coordinates of B the coordinates of A. Therefore, vector BA, well, to find vector BA, we just need to subtract from the coordinates of A the coordinates of B. So we're going to have 7 plus 2 lambda minus negative 1 plus 3 mu. And this is, as given by the exercise, 8 plus 2 lambda minus 3 mu. Now, if you do the same with this minus this and this minus this, you get the lambda minus mu and the 3 plus lambda minus 2 mu, which was also given by the exercise. Therefore, we found the vector BA. So this one is done. Let's move to exercise C now. Find the values of lambda and mu for which BA is perpendicular, and this word right here is very important. Perpendicular means that it forms a 90-degree angle. If it forms a 90-degree angle, whenever you see perpendicular, your mind should go back to dot product. It's usually the case that we use dot product either to prove that two vectors are perpendicular, or the exercise is wrapped around the fact that these vectors are perpendicular, right? Which is this case. Now, BA is perpendicular to both L1 and L2. The dot product of two perpendicular vectors is equal to 0. Therefore, BA dot the direction vector of line 1, which is 2, 1, and 1. Where did I take this from? Well, this is the direction vector to 1, 1 of line L1. This should be equal to 0, and also BA dot the direction vector of line 2, which is 3, 1, 2. It should also be equal to 0. Now, you're going to form two equations whenever you do this. These two equations, they will have two unknowns, so it will be possible to work it out, to solve it, okay? So let me replace BA by what BA actually is, which is 8 plus 2 lambda minus 3 mu, and so on and so forth. All right, so the dot products, they're equal to 0. The two equations they're going to form, they are, and let me move this right here because we have more space over here. And the equations that you're going to form are 6 lambda minus 9 mu equals negative 19, and this is after you simplify, of course, and 9 lambda minus 14 mu equals negative 30. You can use your GDC to solve this. This is a paper 2 question. Your lambda will be equal to 4 over 3, and mu is equal to 3. Notice that we just found the values of lambda and mu for this vector BA over here. Let me use another color. This is our BA. How do we find the actual coordinates without lambda and mu? Well, we can just replace lambda and mu over here in these 6 places. If we do so, we get 5 over 3, negative 5 over 3, and also negative 5 over 3 in the last coordinate. Now, if you wanted to find the minimum distance between these two lines, you could, and this is not something that the exercise will ask, at least that's what I remember. So the exercise does not ask us for that. But if we wanted to do that, the only thing that we needed to do after this is to find the magnitude of this factor right here, which means the root of 5 over 3 squared plus negative 5 over 3 squared plus negative 5 over 3 squared. But again, this is not something that's asked by this exercise. What we do need to find, however, are the points A, and we can find point A by replacing our lambda, which is equal to 4 over 3, into these equations. So we get 29 over 3, 10 over 3, and 10 over 3 as the z coordinates. Now for B, we just need to replace mu equal to 3. In this case, that's the mu that we found, into these equations. So we get negative 1 plus 9, which is 8. So these are the coordinates of B, 5, comma, 5. Now for the last one, we need to write down the parametric equations of P. So in a nutshell, we're creating the equation of this line right here. We already have its direction vector. We can use this, or we can use a multiple of this, given that all of these coordinates they have 5 over 3 on them, so we can just use 1, negative 1, negative 1. It gives us the same direction. We can divide all the coordinates by the same number, in this case 5 over 3, and we can use a point that this line crosses. We could use, for example, this point B right here. Therefore, we get x, y, and z equal to coordinates of point B, 8, 5, and 5, plus the direction vector, which is 1, negative 1, and negative 1. We cannot use lambda or mu because that's taken, so you can use gamma, for example, for our parameter. So that is it. This is the end of exercise number 3. All right, let's get to exercise number 4, one in statistics and probability. Your partner takes a long time getting ready, and on several past occasions, this has caused you to miss dinner reservations. Wow, that's pretty annoying. Based on data you have collected, the time your partner takes to get ready is normally distributed with a mean of 42.8, and the standard deviation is 3.2. So let's first illustrate that using a bell-shaped curve, which is typical of a normal distribution. So we have our normal distribution here. And by the way, not only the mean and the standard deviation, but you should also place right here, or right here, the continuous random variable that you're measuring. In this case, it's the time that it takes for your partner to get ready. So we have time taken to get ready in minutes. Question A is pretty easy. How long does it take for your partner to sorry, not how long, but what is the probability that it takes 40 minutes or less for your partner to get ready? So this is just a normal CDF. We're finding the area under this curve from negative infinity all the way to 40. And if you're using the TI-84, the command looks like this. Normal CDF, negative 1E99, which represents negative infinity, all the way to 40, and the mean is 42.8, and the standard deviation is 3.2. Do know that we input into the calculator the standard deviation, not the variance. We should get, or you should get, 0.191 as the answer. And by the way, you can also express n as a normal distribution with a mean of 42.8, comma 3.2 squared. Do know as well that this represents the variance. The variance is 3.2 squared, which is 10.24. We don't write it like that, 10.24. We write 3.2 squared, so we can clearly see the standard deviation because that's what we use in these calculator commands. Now let's move to question B. On 4 separate evenings, find the probability that on at most one of them, your partner takes longer than 45 minutes to get ready. If you're sensing binomial distributions, you are correct. The first thing we should find is the probability of your partner taking 45 minutes or more to get ready. So we're finding first this area right here, the probability of x being greater than 45, which is approximately 0.246. Do know, however, keep in mind that we're going to use this value right here as the probability of success for the binomial distribution. Don't round to the value before you actually get the answer for question B. So you're going to use 0.24588 ... for the probability of success. If we're changing distributions, we're going from a normal to a binomial, we got to name it something different. Instead of capital X, we're going to name it capital Y, and we're going to define it right now. Y is the number of times out of 4 that your partner takes longer than 45 minutes to get ready. And Y is a binomial distribution, or follows a binomial distribution with the number of trials of 4 and probability of success 0.246. I'm going to write 0.246. However, when we plug it into the calculator, we're not going to round it. Now, how do we know that this is a binomial distribution? First of all, we have 2 outcomes, either a success or not success. Success represents getting ready, taking longer than 45 minutes to get ready. So that's the probability of success. It doesn't have to imply that it's a successful event, meaning it's not a good thing taking so long to get dressed. I don't think that's a good thing. But we can just name it probability of success. The other, or the complement of that, is the probability of no success, which is 1 minus 0.246. But we deal with probability of success. So let's consider, long story short, success being taking longer than 45 minutes to get ready. We also have the probability of success not changing, so it's always that, and the events being independent. Now, we want the number of times out of 4 that our partner takes longer than 45 minutes to get ready to be less than or equal to 1. So at most once. So we're going to do a binom CDF, which is the one that accumulates from 0 to 1, meaning 0 successes and 1 success, where the number of trials is equal to 4. The probability of success is 0.2458 ... And we're going to go from 0 to 1. In this case, or for this case, we get 0.745 as the answer, meaning there's a 74.5% chance that at most once your partner will take longer than 45 minutes to get ready. All right, so let's move to question C, the most interesting one of them all. It is now 7:10. And you have dinner reservations for 8 p.m. This is, of course, a 50-minute gap. Your partner will start to get dressed right now. We know that driving to the restaurant takes 8 minutes. However, your car fails to start 20% of the time, which is quite high. And if that is the case, you need to use a rideshare app, and the total time to get there increases by 5 minutes, which is the time that you're waiting for the driver to arrive, and then you leave. Find the probability that you arrive at the restaurant by 8 p.m. sharp. Now, as we mentioned, we have a 50-minute window. And there are 2 possible scenarios here. Number 1, the car does not fail. And scenario number 2, the car fails to start. what are the probabilities associated to this? The car fails 20% of the time and does not fail 80% of the time. If the car does not fail, you have 50 minutes, or your partner has 50 minutes minus the 8 minutes to get ready, to get dressed. So that means that your partner can take at most 42 minutes to get dressed. However, if the car fails, we have 50 minus 8 minus 5, which means 37 minutes in total. And this is, of course, at most. So the probability of arriving on time is 0.8 times the probability that your partner takes less than or equal to 42 minutes to get dressed, or 0.2 times the probability of taking less than or equal to 37 minutes to get dressed. And given that this and this, they are 0.4012 ... and 0.0349, we get in total 0.3280 ... So rounded to 3SF, 0.328 as the probability that you will get the table on time. Or not get the table, but actually arrive at the restaurant by 8 p.m. So let's move to the next exercise now. All right, so on to the last exercise ever, Calculus 1, given that it's exercise number 5. So an exercise from topic 5. We have a function, which is this. And in question A, we're going to differentiate it using both the quotient and the chain rule. The chain rule, of course, being the ln of 4x. Do remember that if we have u over v, let u and v be these two functions, then u over v prime is u prime v minus uv prime over v squared. Now u prime is 1 over whatever's inside the ln, which is 4x, times the derivative of the inside function, which is 4. Therefore, the derivative is 1 over x. And for v prime, we have a constant multiplying x, which means that v prime is just that constant. In this case, it's k. Now, keeping that in mind, we have 1 over x times kx minus u times v prime over v squared. We can simplify the x's here, which gives us this, but also factor out a k from the numerator, so we can simplify with the k from the denominator. There you go. Now we get 1 minus ln of 4x over kx squared, which is exactly what was given by the exercise. So now we can jump to question B. There's a maximum point at P, and we know that to find maximums, we take the first derivative and make it equal to 0. So we have 1 minus ln of 4x over kx squared, which equals 0. We cross multiply this, it disappears. 1 minus ln of 4x equals 0, which means that ln of 4x is equal to 1. Given that ln is a log base e, we have for x equal to e to the first power. Therefore, x is 1 over 4 times e, or e over 4, which is, of course, the same thing. Now, we were given the second derivative, which saves us a lot of time. Finding this second derivative, finding another derivative, given that we would need to deal with a quotient, would take some time. So we bought ourselves some time here. Now, Q is the point of inflection of f of x, and we do find points of inflection when we take the second derivative and make it equal to 0, which means that we're going to take this 2 ln of 4x minus 3 over kx cubed and make it equal to 0, meaning that we have 2 ln of 4x minus 3, which equals 0, so ln of 4x equal to 3 over 2, which means that 4x is e to the 3 over 2. Therefore, the x-coordinate of the point of inflection is 1/4 e to the 3 over 2. Now, the region R, enclosed by the graph of f, the x-axis and the vertical lines through the maximum and through the point of inflection, has an area of 4. And we know, by the way, that the x values here are 1 over 4 times e and 1 over 4 e to the 3 over 2. We need to find, based on that, the value of k. Now, areas can be found using integration. So we're going to integrate from 1 over 4 of e to 1 over 4 e to the 3 over 2. The function itself, ln of 4x, over k times x dx, and this is equal to 4 according to the exercise. And to make this even simpler, you can move this k, given that it is a constant, to be outside of the integral, given that if you multiply ln of 4x over x by 1 over k, you get the original function, which is ln of 4x over kx. K is just a constant, just leave it outside. Now, this is an integral that we can evaluate through substitution. We can call u ln of 4x, and we know that du, we found it before, it is 1 over x dx, which means that it shows up right here. So this is our du. Don't forget to replace the upper and the lower bounds. For x equal to 1 over 4e, our new u will be ln of 4 times that. So ln of e, which is equal to 1. So this should be 1. Now for x equal to 1 over 4 e to the 3 over 2, our u is ln of 4 times 1 over 4 e to the 3 over 2, which is ln of e to the 3 over 2, which is just 3 over 2. So we have 1 over k integral from 1 to 3 over 2 of u du. And this is all equal to 4. We can cross multiply the k, so we have the integral equal to 4k, and we get u squared over 2 from 1 to 3 over 2 equal to 4k. So 3 over 2 squared over 2 minus 1 over 2 times 1 squared over 2. Perdão, Léo, errei aqui, deixa eu fazer de novo. So we have 1 over 2, 3 over 2 squared minus 1 squared equal to 4k. So half 9 over 4 minus 1 equal to 4k. Replacing 9 over 4 minus 1 by 5 over 4, we get our k equal to 5 over 32. And that is it. We're done. You did it. You see? You did it. You stayed here all 10 weeks. You've practiced with all 10 exercise lists. You did all 10 weeks of this challenge. You're in a very good position on performing super well in your IB math exams. I wish you best of luck. Don't get anxious, don't get nervous. I know, easier said than done, but let me just say there's no reason for you to get nervous, to get anxious, because you've studied and you've studied a lot. So best of luck in your IB math exams, and thank you for staying with me all this time. I wish you well.